Before we start doing some more derivatives of our exponential and logarithmic functions, I just want to quickly remind you the value of e. So e is that irrational number between 2.71 and 2.72. So just like pi, it's transcendental, meaning it will never end. It will just keep going and going. The last thing that I wanted to remind you about is y is equal to e to the x. Its derivative is the exact same. Now, obviously, when we add some more rules in there, it's not as easy as just writing e to the x. So, I mean, if our exponent is changing to anything other than x, it does get a little bit trickier, and that's why we're going to go through some more examples. Before we move on, I did just want to also mention that we can define e in a different way, and it's not really that important now, but I did just want to get you to at least think about it. So we can define e as the limit as n approaches infinity of 1 plus 1 over n to the power of n. Now again, not important right now, just wanted to throw that out there before we move on. Over the next couple of minutes, we're going to be going through some identities for our exponential and logarithmic functions. So I've just used the exact same diagram that I used on the previous video. So we have our function y is equal to e to the x in red, and our blue function is y is equal to ln x. Now, you should remember that they are inverse of each other, so that reflection in the line y is equal to x. So I just have a little note on the right-hand side here that says for all x, if y is equal to e to the x, y will always be positive. So basically, y is always going to be above 0 for that function y is equal to e to the x. And likewise, if we have that function y is equal to ln x, x cannot be less than or equal to 0. So if you try and plug ln of a negative number or ln of 0 into your calculator, you will get an error because it is impossible for that to happen. The following identities are identities that you would have been comfortable using when you took functions, so grade 12 functions, whether that be last semester or concurrently this semester. I am just rewriting them and just reminding you about these identities before we move on. So when we're looking at these identities, the first one says ln of e to the x is just x. Now we know that anytime we're writing ln, it really means that there's that imaginary base e that we just assume and we don't have to write. So we have ln of base e of e to the x, and those are basically just canceling each other out to give us our x. Same thing with the second one. We have e to the power of ln x. Again, we know that these are inverse functions, so we can just imagine the e and the ln canceling each other out, leaving us with our x. The last two are ones that should be easier to remember. So ln of e is equal to 1. Again, that ln has a little base e. And the last one, ln of 1, is equal to 0. So if you think about that graph, we know that we had e to the 0 is equal to 1. And that's basically how they're getting this inverse identity right here. You might be wondering why I'm going over these again. You learned them in the previous course, but sometimes it's going to be easier for us to think about these either before we do a derivative to simplify an equation or after we do a derivative to simplify our answer. So 3 more properties that you've already discussed in great detail. I'm just refreshing your memory. If we have ln of x times y, so a product here, we know that that's the exact same as ln of x plus ln of y. The same goes when we have a quotient, so ln of x over y, that's going to be ln of x subtract ln of y. And finally, if we have ln of x to the power r, that r can go down and we're going to be getting r ln x. So just to quickly refresh your memory about those derivatives that we've talked about already. So the derivative of e to the x is simply e to the x. The derivative of ln of x is 1 over x. And we're going to be adding a new one in here. So the derivative with respect to x of b to the x, so some base b, is equal to b to the x times the ln of b. Now, technically, we can think about e to the x when we're doing this. So if we had the derivative with respect to x of e to the x, we could write it as e to the x ln of e, but we already talked about the fact that ln of e is just 1, and that's why we're allowed to have this rule right here. So our first example says solve for x. So ln of x is equal to 8. I'm going to quickly talk about two different methods to do this. Now we know that since we see a ln, there is that base e here that we just assume. So since I know that, I can just simply say that e to the 8 is equal to x. And I can leave that like that. That's an exact answer. The second thing that I could do is I could take the left side and the right side of this equation and I could raise it to the power of e. So what I could do, sorry about that, is I could say e to the power of ln x is equal to e to the power of 8. And I know from the rules on the previous, well, 2 slides ago, e to the ln x is just equal to x, and then e to the 8 we would leave like that. So same answer, two different methods. It does not matter which method you choose. Now looking at this example, I have e to the power of 3 minus 2x equals 4. If I take the ln of both sides, keeping in mind that ln and e cancel each other out, I would get ln of e to the 3 minus 2x is equal to ln of 4. And I'm allowed to do that. I did that to the left and right hand side, so I'm not really changing anything. I know that the ln and the e are going to cancel each other out, so basically I'm going to be left with 3 minus 2x is equal to ln 4. And I'm going to go ahead and I'm going to isolate my x here, so ln of 4 minus 3, divide both sides by negative 2, and I get x is equal to ln 4 minus 3 over negative 2. This last example is going to be the hardest example that I would ever ask you to solve using something that is involving e to the x. So what we see here are we have a couple of constants, or sorry, a couple of terms that involve e to the x and a constant. And so when you see something like this, we're going to be multiplying everything by e to the x, and you're going to see what happens here when I do that. Okay, so as you can see, I've multiplied each of these terms by e to the x. So e to the x times e to the x minus 12, e to the negative x times e to the x equals negative 1 times e to the x. Now, I'm going to go ahead and simplify this. So I have e to the x times e to the x. I know that that's just e to the x squared. Minus 12, e to the x times e to the, e to the negative x times e to the x, we're going to get a negative x and a positive x, and that's going to cancel out to be 0. So really, these two terms just cancel each other out. And then I'm going to be getting equals a negative 1e to the x. Now what I'm going to do is I'm going to go ahead and I'm going to take this term on the right hand side and move it. So e to the x squared minus 12 plus e to the x equals 0. At this point in time, I'm going to let a equal e to the x, and if you haven't already seen y, you'll see y in a minute. So I'm going to have a squared, I'm just going to rearrange these two, switch these up, plus a minus 12 equals 0. So I can easily see that now I can go ahead and factor this. So I've got a plus 4 and a minus 3. Now if I go ahead and I replace that a, I really have e to the x plus 4 times e to the x minus 3 equals 0. So if I want to go ahead and solve these, what I have here is e to the x is equal to negative 4, which means that x is equal to ln of negative 4, which we know does not exist. And then e to the x is equal to 3, so x is equal to ln 3 is my one and only solution to this problem here. So we're going to be going through and finding some derivatives now. So my first example, f of x is equal to e to the 5x squared. Now, when I'm taking the derivative of e to the x, I know it's just e to the x, so this is going to stay e to the 5x squared, but I also need to multiply through by the derivative of this exponent here, so 10x. Now, it is good form to be putting this out in front, so 10x times e to the 5x squared. If you wanted to go right from this line to this line, I am absolutely okay with that, and we could be skipping this middle step right here. So here we have a product rule, x ln x. So if I'm taking the derivative, it's the derivative, I'll backtrack here, I've got one term here and one term here, one function there, one function there. So the derivative is the derivative of the first times the original second plus the derivative of the second times the first. So if I'm going to simplify this, I've got ln x plus 1. So for my last ln example, I have ln of x squared plus 2x minus 5. So when I take the derivative, I get 1 over all of that, so x squared plus 2x minus 5. But I still need to multiply by the derivative of this, and that's going to go in my numerator, so a 2x plus 2. And so when I simplify this, I get 2x plus 2 over x squared plus 2x minus 5. So for this last example, it's a complicated one. I'm only going to get you to do that first line. I don't care about the simplifications here. If you look right away, you're going to see that I am going to be using my quotient rule, and then inside of that quotient rule, I am going to be using the product rule as well. So what I have here is f prime of x is equal to the derivative of the top. So when I'm deriving the top, I am using my product rule. So I've got the derivative of that first function, the e to the x cubed, so that's just e to the x cubed times the derivative of my x cubed, so 3x squared, and we need to multiply that by our original second function, so that 2x, plus the derivative of that second function, so that's just 2 times the original first function, so e to the x cubed. And we need to multiply all of that by our bottom function. This is where the quotient rule is taking place. And I'm absolutely running out of room. Subtract the derivative of the bottom function, so 5 times the original numerator, or the original first function. And then all of that needs to be divided by the bottom function, so the 5x plus 1 squared. Now again, this is a very hard example. There's no simplification needed. We're just going to stop here at that first line because we're not doing anything else with it.